This video summarizes a master thesis about monocular depth estimation with generative adversarial networks, submitted at the University of Applied Sciences and Arts Northwestern Switzerland. There are different methods to estimate the depth. There are active sensors and passive methods. However, all these methods present challenges. They require expensive sensors and computing resources to generate the depth maps, multiple images to calculate the poses, or a large basis in order to obtain good stereo images. Here comes into play the monocular depth estimation. As our DEB cameras are more ubiquitous than other sensors and less expensive, the collection of the images is much easier. The extraction of the depth is done in this case using a neural network, which estimates it directly from a single RGB image. The following goals has been set for the research. Different sensors and instruments have been used to collect the data: a terrestrial laser scanner, a smartphone with a time-of-flight camera, another one with a LiDAR sensor, and a dataset collected with multiple fixed cameras on a railway construction site. The depth maps collected with the LiDAR needed upsampling. To this end, a joint implicit image function has been applied, which uses a neural network to improve the bicubic interpolation, avoiding the creation of artifacts. For the extraction of the depth map from the fixed camera's dataset, Metashape has been used, which allows to automate all the steps of the process to extract the depth maps. The spherical data collected with the terrestrial laser scanner have been transformed with an equirectangular projection in order to obtain planar images. The depth maps generated with the time-of-flight camera influenced negatively the accuracy during the training. For this reason, those samples have been excluded from the dataset. Once the dataset was ready, the structure of the generative adversarial networks has been implemented. It consists into two competing networks that are trained simultaneously. While one network trains a generative model that uses the data distribution to generate samples, the other one trains a discriminative model that estimates the probability that a sample came from the training data rather than from the generator. To reduce the training times and the learning gap, transfer learning has been adopted, while to improve further the dataset during the training, a data augmentation function has been implemented to virtually increase the dataset. Another challenge with small dataset is the risk of overfitting, causing a poor generalization of the model. In this case, an early stopping function has been adopted to avoid overfitting. To improve further the generalization of the model also on other scenes, additional open-source datasets have been used, training a second model on the new data. While on the original test set the two models perform very similar, on the extended test set the new model demonstrated to have an improved generalization. The resulting depth maps present good structural consistency in comparison to the ground truth, only small ledges and details are blurry or missing in the estimation. To improve the details and edges in the depth maps, a double estimation has been implemented. A first estimation with low input resolution is carried out. Then a maximal input resolution is calculated, using the edge map of the image to ensure that contextual cues are not too far apart. With the calculated high resolution, the second estimation is executed. Finally, the two estimations are combined together using a pre-trained 10 layers UNet. The methods improve the details in the estimations. The double estimation can deliver even better results than the depth maps collected with low-cost sensors. To increase further the level of detail in the estimations using a higher resolution, the image is tiled into patches with the dimension of the receptive field of the network and 1/3 overlap. Then the patches are filtered according to the gradient density and enlarged until they reach the same gradient density than the whole image. Finally, the double estimation is applied to each patch and the results are combined together with the merging network. The resulting depth maps show additional details and objects in the background that weren't defined in the double estimation.